Hello everyone, this is Mr. Sullivan. Today we're going to continue our conversations on logarithms, focusing on the properties of logarithms. I want to start by looking at a definition that Mrs. Greenman showed you the other day that states that the log base b of x equals y if and only if, and that's what this IFF means, if and only if b to the y power equals x. What I want to focus on is that, notice that the logarithm is equal to the exponent in our second equation. Okay, the logarithm is equal to y. Another word for equals, we know, is. And so if you think about it, a logarithm is just an exponent, right? The log base b of x is equal to y, and y is the exponent. And if that's the case, then the properties of logarithms should mirror the properties of exponent. What I've done here is listed the properties of both exponents and logarithms, and we can see the relationship between the two. These properties of exponents you learned back in Algebra 1. When we multiply bases, we know that we can add the exponents. So when we multiply x to the a power times x to the b power, we get x to the a plus b. Well, let's take a look and see how that manifests itself with logarithms. If we have the log base b of m times n, okay, so notice that we have multiplication. Then we can expand that and say that that is the log base b of m plus the log base b of n. When we had multiplication, we added the exponents. When we have multiplication, we add the logarithms. But what is a logarithm? A logarithm is an exponent. Let's take a look at an example. Here I have the log base 4 of 18. Well, another way I could write 18 would be the log base 4 of, let's say, 3 times 6. If I wanted to expand this logarithm, because it's multiplication, I could add the logarithms. I could add the exponents. So the log base 4 of 3 plus the log base 4 of 6. Remember, a logarithm is an exponent, and so we're showing the property here by adding the exponents. Let's go back to the properties of exponents. When we had division of the bases, x to the a divided by x to the b power, what did we do? We subtracted the exponents. Well, the quotient property of logarithms says that when we have division within our argument is m over n, that we can subtract the logarithms, the log base b of m minus the log base b of n. Again, what is a logarithm? A logarithm is an exponent, so it makes sense that we're subtracting the exponents here. Again, let's take a look at another example. If we had the log base 5 of 2, another way that I could write that, let's say, is the log base 5 of 12 over 6. I'm going to say 2 is equal to 12 over 6. Well, how could I expand this logarithm? Again, subtract the exponent. So this becomes the log base 5 of 12, that's an exponent, minus the log base 5 of 6. Finally, we learned the power to a power property back in Algebra 1, and it said if we had a quantity that was with an exponent that was raised to a higher power, we would multiply the exponents. X to the a power raised to the b would become x to the a times b. Well, again, let's take a look at the log property. If we have a log base b of m and the argument has an exponent, what we can do is we can take that exponent and move it to the front of the log. And you can see it here on the right. The x has been moved to the front of the log, and that gets multiplied by the log base b of m. Well, what was x in the original problem on the left? It was an exponent. What is it being multiplied? It's being multiplied by a log, which is an exponent. So again, what did we do here? We multiplied the exponents. An example would be if we had the log base 5 of 8, we could rewrite this as the log base 5 of 2 to the third power, right? Because 2 to the third is equal to 8. Well, what can I do with that exponent, the 3? I can move it in front of the log and rewrite this as 3 times the log base 5 of 2. Now, these properties are going to be very useful to us in helping us solve equations that involve logarithms and exponential equations. Today, we're going to practice them using some other examples, and we'll take a look at those in a minute. But I just want to talk to you about a couple of other important facts. You'll notice that down here I have another property. It says the log base b of b is equal to 1. And why do we know that's true? Well, remember, Mrs. Greenman showed you how to convert from log to exponential form. So I'm going to go ahead and do that. And if I do that, I get b to the first power is equal to b. I'm converting that log equation into an exponential equation. Well, does this make sense? Of course it does. If we raise any quantity to the first power, it's going to be that quantity itself. So b to the first power equals b. So the important thing for you to recognize is anytime you see a log whose base and argument are the same, that will automatically simplify to equal 1. For example, the log base 7 of 7, that's equal to 1. The log base 13 of 13, of course, it's going to equal 1. The log base 1002 of 1002, well, again, that's going to equal 1. And finally, one last important fact that Mrs. Greenman introduced the other day, but I just want to reiterate. Remember, if you see the word log written without a base, so if we see the log of 14, okay, where 14 is the argument, but there's no base, the base is missing, we can assume that that base is 10. So if we put that thought together with our previous thought, if we see the log of 10, what would this simplify to be? Well, again, anytime a log is written without a base, we can assume it's a base 10. And if it makes you feel more comfortable, you can put a little 10 in there as the base. Well, we know then, since the base and the argument are the same, that this is going to simplify to equal 1. Okay, so let's take a look at how we might see these properties in action. I've given you some logs here, and actually if you had taken your calculator and typed in the log of 2, you'd get a number that's not exactly equal to, but approximately equal to 0.301. And again, what does this mean? This means that if you raise 10 to the 0.301 power, you're going to get 2, okay? Again, approximately 2 because it's not exactly 0.301. Okay. Same thing if we raise, if you type log of 3 into your calculator, you're going to get 0.477 because 10 to the 0.477 power equals 3. And for the log of 7, you're going to get 0.845. Now, I'm asking you to evaluate these logarithms, the log of 14, the log of 42, 9, 7 halves, and 30. And what we're going to do is we're going to use the log properties that we learned up above in order to help us calculate these logarithms. Now, here's one thing I want to strongly emphasize. Anytime you see these log problems where you're given some values and you're asked to find some other log values, the very, very first thing I want you to do is to go and identify what the base of the log is. So when we look at these given logs, we notice that there is no base, and so therefore we know that these are base 10. What I want you to do is to write down the log with the exact same argument as the base that you're given. So in this case, I'm going to write down the log of 10. Now, what does the log of 10 equal? We know from up above that the log of 10 is equal to 1. So this is sort of an additional given value. In addition to the log of 2, the log of 3, and the log of 7, we now know the log of 10. Okay, so let's tackle some of these problems. First thing we're going to want to do is to break the argument up. What I mean when I say break the argument up, take your given values, the 2, the 3, the 7, and the 10, and try to rewrite this value, the argument's value, using only the operations of multiplication, division, or one of those numbers raised to a power. Why only those operations? Because, again, those correspond to the properties that we were given up above. So when I rewrite the log of 14, I'm going to break the 14 up, and I want to use the product, quotient, or one of the given numbers to a power. So I'm going to rewrite this as the log of 2 times 7. Now, the log of a product property says that I can then break this log up into 2 separate logs. I can rewrite this as the log of 2 plus the log of 7, right? That's this property right here. Now, log of 2, I know what that value is. That's 0.301. Plus the log of 7, which is 0.845. And I'm getting these values from up top here. So if I add those two together now, I'm going to get 1.146. And so therefore the log of 14 equals 1.146. All right, let's move on to number 2, the log of 42. So we need to break up 42 as the product or quotient or one of these given bases raised to a power. 42 is 6 times 7, or 2 times 3 times 7. So I'm going to break this up as the log of 2 times 3 times 7. So I'm just rewriting my argument initially. Now again, I'm going to use the log of a product property to expand this logarithm, and I'll use addition of logs. So the log of 2 plus the log of 3 plus the log of 7. Substitute in their given values, 0.301 plus 0.477 plus 0.845, and we get 1.623. And that's what the log of 42 equals. Okay, log of 9. I'm going to approach this a little bit of a different way. Of course, we could rewrite 9 as 3 times 3, but another way to rewrite 9 is 3 squared. So again, I'm using those given values. Now, the log of a power property says that I can then take this exponent and move it in front of the log. So that's going to equal 2 times the log of 3. Now I can substitute in the given value for the log of 3, which is 0.477. So this is going to be 2 times 0.477. If I simplify that, I find that the log of 9 is equal to 0.954. Okay, log of 7/2. I see some division there, so it looks like we're going to use the quotient property. So if you remember, the quotient property says that when we have division within our argument, we're going to subtract the logarithms. So I'm going to rewrite this as the log of 7 minus the log of 2. Well, again, substitute in your given values. 0.845 minus 0.301, and we'll get 0.544. Now, guys, I really want you to be careful on division, because that's where students most commonly make mistakes. For some reason, they still divide those values. They might divide 0.845 by 0.301. Remember, division in the argument means subtraction of your logs. Okay, now let's go to look at the next example, which is the log of 30. Now, if you looked at our original group of givens, 2, 3, and 7, there's no way that you could find a combination of the product or quotient, or even those numbers raised to a power, and get to 30. But that's why we want to identify that the log of 10 is equal to 1, because we can rewrite 30 as the log of 3 times 10. Well, now I can use my log of a product property to break this up. This becomes the log of 3 plus the log of 10. And I'm going to plug in my given values. So 0.477 plus, we know the log of 10 is equal to 1. And so therefore the log of 30 is 1.477. Okay, good. Now I want to take a look at another way you might see these properties in action. I've taken the liberty of copying the properties down here again towards the bottom of the sheet, just so we have them handy. Now, if we take a look at the directions here, it says write each logarithmic expression as a single logarithm. When we say single logarithm, we literally mean we only want to see the word log written once. Okay, common mistake is for students to write that word log more than once. Single logarithm, just write it once. Okay, so here's what I'm going to do. I'm going to actually use these properties. We're kind of going to go in reverse now. We're going to move from right to left, and you'll see what I mean in a second. In problem number 1, I've got 2 log expressions. I want to combine them and make a single log. Well, I see that there's subtraction next to them, so I know I'm going to use my log of a quotient property, but I'm actually going to use it in reverse. When I put these guys together as a single log, I first notice that they have the same base, and that's important. If these logs did not have the same base, we would not be able to use these properties. But in this case, they have the same base, so the properties work. So when I put these guys together, I'll write down the log base 3. What am I going to do with my arguments? Well, if I work this property in reverse, I'm going to divide the arguments. So it'll be 20 over 4. And of course, now we can simplify that. So that'll become the log base 3. 20 divided by 4 is 5. And voila, we're done. Okay, let's take a look at the second example. We've got addition of logs. We want to rewrite this as a single logarithm. So again, I'm going to write down the word log base 4 because they both have a base 4. I'm not going to write that word log again. We've got to be careful there. Now, put these together, it's addition, so I'm going to multiply the arguments, so that'll become 8 times 2 is 16. And we're done. Now, This is just an aside, you could leave your answer this way, but does anybody recognize what the log base 4 of 16 is? If, borrowing from Mrs. Greenman's lesson the other day, if we said this was equal to x, and we converted it to exponential form, this would become 4 to the x power equals 16, and so therefore x would equal 2. Okay, again, not necessary in this problem, but okay, just wanted to bring you back to what the logs really mean. Okay, they're an exponent. The 2 is the exponent. Okay, number 3, let's put this log together. Now we have to use a couple of properties here because we notice that in front of the first log there's a coefficient, there's a 3 there. Well, so again, if I use my log of a power property in reverse, meaning from right to left, that tells me that I can bring this 3 up and make it an exponent for the argument. So I can rewrite this as the log base 2 of x to the third plus the log base 2 of y. So if you're trying to rewrite as a single log, move those coefficients up and make them exponents for the argument. Okay, let's put these guys together here now. We've got this, both logs have the same base, so that's good. So the log base 2 of x to the third y. You can put those guys together using multiplication because it's addition of logs, and we're using log of a product property in reverse. Okay, last one. First thing, again, I see that I've got a coefficient, so I'm going to move that up, make it an exponent. And then I also notice that I've got a combination here of both addition and subtraction, so it looks like I'm going to use all 3 properties in this one. Log of a power to move the coefficient up to the exponent, log of a product to handle the addition, and log of a quotient to handle the subtraction. So again, I'm going to write the word log 1 time. Okay, now here's a little trick that I like to use. Anytime I have a log that's positive, and both the first 2 logs are positive, I put their arguments up in the numerator. So this will become 5x squared, right? Don't forget we moved that coefficient up and made it x squared. Anytime I see a log that's negative, I put its argument in the denominator, so over 10. Okay, I can simplify this. This becomes the log base 6 of x squared over 2. And that's my final simplified log. I just want to reiterate that last point that I made. If I have to put together logs as a single argument, if I see a log that's positive, its argument goes in the numerator. If I see, oops, sorry, I meant to make this last one. Let me just fix that up real quick. I meant to make this last one the log of z. It almost looked like a base 7. The log of z. If I see a log that's positive, its argument goes in the numerator. If I see a log that's negative, its argument goes in the denominator. So positive logs are the first and the third, so their arguments go up in the numerator. Negative logs, the second and the fourth, their arguments are going to go in the denominator. And again, I'm only writing the word log once. Okay, don't write the word log for the numerator and the word log for the denominator. Remember, single logarithm. Okay, guys, that was a quick introduction to the properties. You're going to try some practice problems with your teachers now. Best of luck.